So with this video, I'm going to be going over trigonometric limits, right? Normally, whenever you deal with trigonometry and limits, some people think that approaching the squeeze theorem is our best option, but you can clearly see over here that the squeeze theorem is not going to be our best approach. And in this case, let's first evaluate this limit here, right? If we evaluate the limit, we're going to take the limit into all of these ratios over here, into the tan of x, into the sine of x, and the sine cube of x. So we're going to get the following. It's going to be tan of 0, which is equal to 0, minus sine of 0, which is equal to 0, all over our sine cube of x, which we can just write that as sine x all cubed, like this. And then it will be 0 all cubed. And we can clearly see it gives us an intermediate form over here. Indeterminate form, sorry, not intermediate. Indeterminate form over here, which is 0 over 0. So some people would approach L'Hopital's rule. Now, you can try L'Hopital's rule, and I've done it already. I've tried it. And what you will see is that it won't work with L'Hopital's rule. It will constantly be indeterminate every single time because you will always get 0 over 0. So let's try a different approach. Let's do this. So I'm going to try and clear this up so it's easy for us to see. Now let's do this, right? We know in limits, sometimes if we want the limit to have a value, sometimes we need to maybe simplify algebraically, basically. So what I'm trying to say is we need to use identities to try and make this solvable, this limit solvable. So that's what we're going to do right now. That's what we're going to be doing right now, sorry. Okay, so we have the limit as x approaches 0, and then our bracket here. We actually don't need to write the bracket, so I won't write the bracket. We have tan of x minus sine of x. Now what I want to do first is let's consider this tan of x. We know that the identity could also be written as sine of x over cos of x. So let's write it like that. So we have sine of x over cos of x minus sine of x. Okay, and all over sine cube x. Okay, now that's our first step over here. The second step that we are going to be taking over here is that we are going to write this like, so I'm going to just change it over here, if you don't mind. I'm going to write it like this. It's actually going to be sine x multiplied by 1 over cos of x. We're going to just take the sign out of the fraction and we're going to write it as multiplied. And we can clearly see over here that we have a common factor of sine of x. So we can take sine of x as a common factor. So let's do that. We have sine of x, and then we have 1 over cos minus 1. And this is all over. Remember, we still have a denominator here. This would be all over sine cube of x. Okay. And now what we can do over here, we can clearly see that we can now cancel the signs out over here, but this will be sine square x now. So let's do that. Now, and then this is going to be 1, which we basically just disregarding it right now. So limit as x approaches 0, and we have 1 over cos x minus 1. So what I'm going to write down over here, if you were to try and substitute from exactly what we have here, so let's say we have 1 over cos of x, so let's say cos of 0 for now, we're substituting in for the x, minus 1, and well, this is all over sine of square x, so it's going to be sine square of 0, which we know is going to be 0. Over here, this whole thing in the numerator, it'll be what is 1 over cos of 0. We can also write this as sec of 0, by the way, which we know that according to our sec graph over here, we have the following over here, and then we have this over here, where these are in line with negative 1, and this would be positive 1 over here. It's basically just our cos graph that looks like this. Okay. And we know that the value of cos of sec of 0 is just equal to 1, which we can clearly see that's going to be 1 minus 1, which is equal to 0. And that's going to give us 0 over 0. And that's why we need to continue simplifying. And that is why we can't immediately simplify from this point. So let's keep simplifying and see if we get somewhere. So you will probably be, a lot of students would be lost at this point, right? So what I'm going to be doing is I'm going to write it like this. So we have 1 over cos of x, and then we're going to say minus, and note, okay, take this in note over here, right? 1 can be written as anything as long as it divides itself as long as it's divided by itself. So we can write x over x. 1 can be represented as x over x, or it could even be represented as sine x over sine x, as long as the two numbers are exactly the same on the numerator and the denominator. And what we want to do is we want to actually make this a single fraction. So in order to do that, we can write 1 as cos of x over cos of x. And note now that what we have is we have two denominators here that are exactly the same. So we can just integrate them into one denominator. Sorry, maybe let me not use integrate, because I think some calculus 2 students would think like, hey, what are you talking about, Dylan? Okay, so it's the limit as x approaches 0, and then we can just write this as one fraction. 1 minus cos of x all over cos of x. Okay, all over, and then we have sine square of x. Cool. And now from this point, we can just tip in times. We know that this is actually sine square x over 1. So we're just going to tip in times, and we're going to write it like this. It's going to be the limit as x approaches 0. And then it's going to be written as, let me just write it like this. So it's actually written like 1 minus cos of x all over cos of x multiplied by the inverse of this, which is going to be 1 over sine square of x. So then we can just multiply the numerator with the the denominator with the denominator and the numerator with the numerator, and we'll get 1 minus cos of x all over, this thing is bugging out, I apologize, all over cos x multiplied by sine square x. So cos x multiplied by sine square of x. And that is what we have right now. Okay, so if we still simplify, and I'm just going to show you right now, even if we simplify from here, we're still going to get it in indeterminate form. We have 1 minus cos of 0, which is equal to 1. And we know sine of 0 is just going to be 0, and 0 multiplied by anything will still be 0. So we'll still get 0 over 0, right? I know I went fast, I apologize, but I'm running through this because you can even try it yourself. You can try and substitute, and you'll see, you'll get 0 over 0, which we still do not have our answer. But what we can do is the following. We know that sine square of x, let me get rid of that, can also be written as, so note that we have the following identity, right? We have sine square x falls under the one identity where we say sine square x plus cos square x, which is equal to 1. And if we want to actually replace the sine square x, we are going to do the following. We are going to make cos square x the subject of the formula, or not the subject of the formula, sorry. We are going to make sine square x the subject of the formula, so we can determine what is going to be our new form of sine square x. So we're going to basically just take, or we're going to, let me do this. We're going to minus both sides by cos square of x, and then minus cos square x. Sorry about this. And then therefore, these are going to cancel out here. And then this is just going to be sine square x equals to 1 minus cos square x, which is this. This is our new form of sine square x. So we can write it like that now. Is equal to the limit as x approaches 0, 1 minus cos of x all over. Okay, and then it's going to be written like this. Cos of x multiplied by 1 minus cos square of x. Okay. So I think at some point, I think I was stuck over here, but then I realized something, right? And it's so cool to and this is why algebra has played such a huge impact through high school. This is why algebra was very important, right? To get to this very moment. We literally been in high school for 5 years just to do this exact thing. No, I'm joking. That sounds ridiculous. But let's consider this, right? If we multiply this cos of x into the 1 and the cos of x into the cos square x, we're still going to get a form of 1 minus 1 at some point, right? If you were to, it would be cos of x minus cos cube x, which is still 1 minus 1 equal to 0. But what we can do over here is, let's note that 1 is a perfect square. And cos square x, we can write it as cos of x all square, which means it's a perfect square. So therefore, so I'll write it as a perfect square. So therefore, this is actually a difference of 2 squares. And then we can write it like this. The limit as x approaches 0, 1 minus cos of x all over cos of x multiplied by 1 minus cos square x, so it's going to be 1 plus cos of x multiplied by 1 minus cos of x. Okay, so it's difference of 2 squares. And now, you can clearly see we can simplify even more. We have 1 minus cos of x, and you can clearly see that this can cancel out with this one over here. And this will be 1. And now we simplify even more. Limit as x approaches 0. We are going to have 1 divided by, and now you can clearly see that we don't have to worry about the numerator anymore. But let's just focus on the denominator here. We have cos of x multiplied by 1 plus cos of x. So let's just multiply the cos of x into the bracket over here, and we'll get cos of x times 1, which is cos of x, plus cos of x times cos of x is just cos square x. Now, let's take the limit in. So if we take the limit into a constant, the constant will stay exactly the same, because we know our rule over here. The limit as x approaches a of a constant is just going to be equal to the constant. So which means we're going to have 1 as the numerator, and then we're going to take this limit into these trig ratios here, and we know that cos of x is just equal to 1 plus, and then if you take the limit into the cos square x, remember that's going to be 1 square, and therefore you can see we're getting somewhere here. Therefore the answer is 1 over 1 plus 1 square, which is just equal to 1 plus 1, which is equal to 2. And that is our final answer for the limit.